Hello everyone and welcome to this next video looking at exam questions for the SLAA course. Now today's question involves some calculus. It's taken from section B of paper 1, so no calculator for this one. It comes from section 5 of the syllabus. You can see here we're dealing with some differentiation and understanding the derivative as a gradient, and we're also dealing with some definite integration involving finding the area under a curve. I've given this one 4 stars. It's a little bit tricky, but not too bad. So let's get stuck in. First of all, in this first section, we are given a function, and it's just the normal cubic graph x cubed. So that's quite nice. The following diagram shows the part of the graph of f, and then we're given 3 points along the line P, Q, and R. We're given coordinates for each. Q and R are given numerically, but P is given in terms of A, which is the x coordinate, and F of A, the y coordinate. Now, the first thing I might like to do here is actually just simplify that out a little bit and realize that since F, of course, is x cubed, the coordinates of this point are just A cubed. We're then told that the point P, where A is greater than 0, so A is positive, it's to the right of the y-axis, lies on the graph of f. The tangent at P crosses the x-axis at the point Q, and the tangent intersects the graph f at the point R. So this line is tangent to the graph here and crossing the x-axis here at Q, and then meeting the function again here at R. So as soon as we hear about tangents to curves, we should be thinking about differentiation. We should be thinking about the gradient function. First, we're out to show that the gradient of PQ is. Now, this question is a classic example of quite a common technique in maths, which is to evaluate something 2 different ways, equate them, and then use that to find an unknown. First off, we're asked to find the gradient of PQ, and then we're asked to find f dashed of A. Now, if you know anything about differentiation, you'll appreciate that those should be the same thing. Now, if part 2 is asking me to find it through differentiation, then part 1 is probably asking me to find it in a different way. And a quick glance at the numbers involved in that can give you a bit of a hint. We're going to use the normal gradient idea here, of course, where gradient m is rise over run. That's the change in y divided by the change in x. And I'm just going to zoom in, just drawing a little diagram here on this section PQ. And we can think again about rise and run here. Now, the coordinates of P, as we discussed, were A cubed, and the coordinates of Q are 2/3, 0. So what I'm going to do is evaluate the rise, that's the change in y, and evaluate the change in x. Well, here I'm simply going from 0 up to A cubed. Sorry, that's a little unclear to see there. So this is going to be A cubed. And as I go left to right here, I'm going from 2/3 to A. So this is going to be A minus 2/3. Then we can simply substitute into our gradient formula here, rise over run. We get A cubed over A minus 2/3. Now, that seems really nice, remembering that this is a show that question. So we just need to make sure we're really clear about how we've done that. You notice I've written out the formula I'm using for gradient. I've then drawn a quick diagram identifying that it's points P and Q that I'm using. I can show clearly that I've used the coordinates here to get these 2 values and then substitute them into a formula here as required. So I feel like I've shown enough evidence there. That should be fine. Really, that's going to be perhaps 2 out of these possible 7 marks. So should be good there. Next, we're asked to find f prime of A. Well, this is the gradient function, remember? F prime, the gradient function. I'm just going to make a little bit of space here so I can get all this on one page. Now, I'll start off by f prime of x. Remember, A is a constant, and so I don't want to directly evaluate f prime of A. I'm going to evaluate f prime of x to get the gradient function, and then I'll substitute A into the function. So f prime of x is just what I get when I differentiate f of x, x cubed, so I get 3x squared, and then I can say that f prime of A is what I get when I substitute in there, 3a squared. So that's part 2 done. And then, like I said, we've counted something, or we've evaluated something in two different ways. One way by using this gradient method and another way by doing the differentiation. Both of those should give me the same thing, because the gradient from P to Q is the gradient of the tangent to the curve at P, and f prime of A is also the gradient of the tangent to the graph at P. So these two things should be equal, and hopefully when I equate them, I should be able to solve and show that A equals 1. Again, this is a show that question, but it shouldn't be too tricky to solve. Now we've got A cubed over A minus 2/3. So a little bit awkward, I guess, in the algebra. All I'm going to do is I'm going to multiply both sides by the denominator of the right hand side, and so I'm going to get 3a squared here times A minus 2/3, which is equal to A cubed. Expanding the bracket on the left hand side, we get 3a cubed minus, now the 3's are going to cancel, and I'm just going to be left with 2a squared, which is equal to A cubed. And I can see here I'm going to end up with a cubic with a quadratic term as well, but since there's only a cubic and only a power 3 term and a power 2 term, this should be fairly easy to solve by factorization. Let me just make a little bit of extra space here so we can give this a proper examination. So we're 3a cubed minus 2a squared, 3a cubed minus 2a squared, sorry, is equal to a cubed. Now, just like when we're solving any quadratics, we want to get everything over one side so that we can use the null factor theorem. So I think here it's probably easiest just to subtract my a cubed term over to the left hand side, and I'm going to end up with 2a cubed minus 2a squared equals 0. And now I'm just going to look for a factor. Well, 2a squared is in fact itself a factor. Here we go, we've got a minus 1 then is equal to 0. And the null factor theorem, remember, tells us that if I have two things that multiply to give 0, then one of them has to be 0. So my two solutions are either 2a squared equals 0. This would lead me to a squared equals 0 or a equals 0. So there's one possible solution. The other is that a minus 1 equals 0, which leads me, of course, to the solution a is equal to 1. All we need to do here is just refer back to the question and have some reason for discarding our solutions. Well, a here is obviously positive because it's to the right of the y-axis, so I can just write a equals 1 since a is greater than 0. So that's the first part done, and as I said, it's a nice classic mathematical method that find two ways of enumerating something and then equate them to solve for an unknown, in this case a. So that's the first part. That's to do with differentiation and understanding the derivative as a gradient. We move on now to section B, which is related but really doesn't require anything from section A to do. So if for some reason you completely forgot about differentiation but remember integration, you could still do part B separately, and it's worth 9 marks. So let's have a look. The equation of the tangent is 3x minus 2. So we're given the equation of this line now, y equals 3x minus 2. And we are given that T is this region here, enclosed by the graph of f, the tangent PR, and the line x equals k. Again, we've got this unknown parameter k. Between x is negative 2 and x equals k. So a lot of language really just to say it's this shaded region, but it's trying to signpost for you the things that you'll need. You'll need to know the left and right limits, so negative 2 and k, and you'll need to know what functions are bounding the area. Now we're told that k is between negative 2 and 1. I mean, that sort of seems fairly reasonable. I suppose if you could take a k value way out here, perhaps we might arrive at another answer, but I think it should just be common sense. So given that the area of T is 2k plus 4, show that k satisfies the equation. So show that questions generally, of course, and remember, just work with the information given try and find the value of this area, and then what we're going to do is come up with an expression for that, equate it to the given value 2k plus 4, and then use that to solve for k. So how do we write an expression for this area? Well, I think it's always good to start with a sketch. So what we've really got is the gap between this function here, y equals 3x minus 2, this function here, which was our original y equals x cubed, and we're looking at this region here. Now, you'll remember that definite integration gives you the area enclosed by a curve and the x-axis between limits. Now, in this question, the x-axis is actually well above our line. So if I was to integrate this curve here, for example, so let me just swap colour. If I integrate x cubed between -2 and k, what I'm going to get is this area here. And I'm just shading it in blue, because it's the area bound by the curve and the x-axis. Even when you're below the x-axis, you're going to get given that area. That's not quite what I want, but it is going to help me find the area of shaded section T. So what I'm actually going to need to do then is evaluate this whole trapezium here, that I'll think of it outline in red, and then subtract the blue area. So I'll need to do this trapezium, take away the blue area, and that should give me what I'm after. So it is worth taking a moment here in exams just to reason really carefully about the area, because if you subtract the wrong thing or you add the wrong part, then you're not going to get the right answer. This is a show that question, so we should know at the end whether we're right or wrong, but just take a moment to think through the logic. We need the area of the red trapezium, subtract the area of the blue region, that's given by an integral, and then we should get the required area. Now, often when you have a straight line as one of your functions here, you're going to probably find it easier to evaluate that area as a triangle or as a trapezium. But in this case, if you look, the lengths of this trapezium are going to be a little bit difficult to calculate because of this unknown value here of k. Then you're going to get an unknown in one of the lengths of the trapezium. You've also got an unknown in the width of the trapezium. So I think it's probably easier to just write this one as a definite integral. So let's go ahead and do that. The area under the the area bound by the red trapezium there is going to be the integral from -2 to k of this function, which was 3x minus 2. And then from that, I'm going to subtract the integral, as I've written up here, from negative, do you know what, let's stick with blue while we're here, why not, from -2 to k of x cubed. Of course, these should both say dx, and that should give me what I want. Now, thinking about the rules we know for integration, sometimes it's nicer to integrate these separately and then subtract, but actually in this case, I think I'm just going to combine this all into one function to integrate. So I'm going to forget about the colors now. I hope that's clear enough at this point. And we're going to integrate from -2 to k of negative x cubed plus 3x minus 2 dx. And now, again, show that, so we want to be really careful with all our steps. I'm going to indicate to the examiner that I've gone from the integral to the integrated form of a function by swapping out the integral symbol now for a big pair of square brackets, and I'm going to integrate each term as I go, so I get negative x to the 4th over 4 plus 3x squared over 2 minus 2x. Again, each term just integrated separately using the power rule for integration, and then my limits are still left here as -2 and k. And so I'm hoping that what happens is, as I substitute k and -2 into these things, I'm going to get an expression. I'm going to equate that to the value given here for t in the question, and that should hopefully lead to this equation here. So let's just head over the page so we've got a little bit more space. We've got the integral of negative x to the 4 over 4 between -2 and k. So working just on this expression, we're going to substitute in k first, and we get negative k to the 4 over 4 plus 3k squared over 2 minus 2k. I'm going to use round brackets for the whole thing here so I don't get confused with signs. I know I'm substituting in a negative 2, and negatives often lead to errors. So let's put this negative 2 in. Well, we've got even powers of negative 2. So actually I can forget about the sign there. Negative 2 to the 4 is going to be 16. And then I've got 16 over 4. So negative 4 for this first part. Then I've got negative 2 squared is 4. Over 2 is going to be 2, and then 3 2's give me 6 here. And then finally I've got negative 2 times negative 2 for positive 4. So let's tidy up what we have here then. We have negative k to the 4 over 4 positive 3k squared over 2 minus 2k, and then this last bit, the 4's cancel, and I'm left with negative 6. Now, according to the question, this should equal, let's just double check, it should equal 2k plus 4. The only slight difficulty with this is we're evaluating an area underneath the x-axis. Now, this expression here corresponds to, if you remember from our previous sort of sketch, we've now got this area here, the region labeled T in the original diagram. Now, the difficulty with that is because the area lies underneath the x-axis, this is actually going to return us a negative version of the area. Now, that's not a massive problem, we just need to be aware of it, because if we're not, the algebra is going to go a little bit wrong in this next step. So what we need to do is take the negative version of what we have to turn it into what is obviously a positive area here. Remember, area is an absolute value. It's always measured in a positive. So when we're discussing the area around curves, we need to use the positive version of this. It's slightly different if we're using this method for things like accrued change. So if you're looking for displacement over time, that kind of thing. But in this case, we're dealing strictly with area. So we're going to be given the positive version of that. So I need to take my expression that I have so far for the area and change the sign of each term, multiply through by negative 1. So we get k to the 4 over 4, negative 3k squared over 2, positive 2k and positive 6, and that is now going to equal 2k plus 4. It's a little bit of a tricky one, that, but you just need to remember that when integration is used under the x-axis, it's going to return a negative area. Sometimes that makes sense in context, but if you're explicitly asked about area, it will always be the positive version of that. So hopefully this now works. If we multiply through by 4, just to get rid of the denominators, we get k to the 4 minus 6k squared plus 8k plus 24 is equal to 2k, is equal to, we must multiply both sides of the equation, of course, 8k plus 16, and now we just need to tidy this up for k to the 4 minus 6k squared. The 8k's cancel each other, and then I'm left with 24, take away 16, which is going to be 8. And I believe that is as was required in the problem. So a little bit of a tricky problem, that one. This little issue with negative area is one of those thorny topics within integration. You just need to be careful about. Be deliberate with what you're doing, and remember that anything under the x-axis is going to give you a negative answer. You want to turn that into a positive if you're asked about area. And that's it. Thanks very much for watching.